All right, let's go to our last problem on the exam. PMMA polymer. So I know my Young's modulus is equal to 1 times 10 to the 9th Pascal. Nu is equal to 0.4. It's bending into the board or into the page. So we don't have a coordinate system here. So let's go ahead and let's add one. So I'm going to say this is my basically one direction, two direction here. We need to make sure, note to self, add one. So this is our one, two direction. So now I know that my stress tensor, I'm going to have a stress in the 1, 1, and it will be this negative. I'll also have a stress in the 2, 2. No other stresses here, except for bending in terms of the normal stresses. There's also stress in the 2, 2, and that's also going to be a negative value here. I will have strain, my strain tensor, strain the 1, 1, strain the 2, 2, strain the 3, 3, and we can kind of see how they're aligned. Now there's also bending strain as well. We're also told we have gauges with a resistance of this. We also have a shunt resistor. Once the switch is closed, we read this voltage. So this is going to be the voltage of the shunt. My strain of my shunt is equal to absolute value minus 1 over F. Resistance of my gauge over resistance of my shunt plus resistance of the gauge. Once we load, it's this. And then finally, thermal expansion coefficient here. Gauge factor, F is equal to 2. And we're asked to write out the strain measured by each strain gauge quantitatively, normal stress and strain tensors quantitatively, bending strain, and solve for essentially all those values. So this is our 176. That's our V sigma. So we know we have this relationship that our strain from the shunt is going to be equal to V sigma over V of the shunt. And that's going to be equal to epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. So let's start to write out these values. But before we do, we can even just kind of start off by saying, we have, actually, let's go ahead and start to get a Mathematica, because I'm just going to solve this. So we know that epsilon 1, 1 is equal to, actually, let's see if I can, let's go over here. Let's take some of these values. So here in this problem, I'm actually going to use this over here. So there's no mention of the change in temperature. So I'm just going to set this equal here. And also, we don't see a stress in the 3, 3. So I'm just going to write out essentially those equations here. If you wanted to do it in the more kind of complete form, it'd be minus nu sig 2, 2 plus sig 3, 3. And we can say sig 1, 1 plus sig 3, 3. And we can actually define that. And we also know that sig, in this problem, sig 1, 1 equals minus 20 times 10 to the 6th. We know that sig 2, 2 equals minus 17 times 10 to the 3 kilopascal. Be careful. All right. We know that the resistance of our gauge is equal to 170. Resistance of my shunt is equal to 185 times 10 to the 3. We know ES is equal to absolute value. Our gauge factor is equal to 2. Basically, here we go, minus 1 divided by F times basically RG divided by RS plus RG. So we can actually see what that value is. Good. So we have our strain. We also have our V of voltage of the shunt is equal to 76 times 10 to the minus 3. Our voltage of sig is equal to 176 times 10 to the minus 3. Excellent. So we also know, and you can always double check to make sure that these values are here. So see, I need to define my y is equal to 1 times 10 to the 9th. My nu is equal to 0.4. We can redefine essentially these values. And we also know that sig 3, 3 is equal to 0. So we've already got our strain in the 1, 1 and the 2, 2 directions. So that's very good. So now the question is, what's the strain that's being felt in these strain gauges? Well, if I look at my E1, my strain in strain gauge 1, I actually have, so that is going to feel what? It's going to feel the strain in the 2, 2 because it's a line in that direction. Now, when I bend that into the board, what is going to happen? So as I bend, if I bent it out, it would pull there. If I pull in, I'm actually going to get a plus nu times E bend. So for that strain gauge 1, because I'm compressing it and it's going to pop up. because that's going to be on the face. So if I'm looking at E2, E2 is measuring E11 plus, if I bend it into the board, that's going to be a whole minus EB. E3 is on the back side, so that's going to be extending if I push it into the board, but it's still E11. That's a line in that direction. So that's going to be plus EB. And then finally, E4 is going to be equal to, so if I push that in, it's going to be the same thing as now E11 plus EB. Excellent. So those are essentially the strains for each strain gauge. So now I'm going to set up my equation where I'm going to say solve ES times V sig divided by VS, set that equal to E1 minus E2 minus E3 plus E4. And it's just going to solve automatically for the unknown, which is just E bend. And there it is. So if that's E bend, so my EB, if that is indeed EB, I have already defined essentially that strain tensor. I've already defined E11, E22, and if you want, you can go through, E1, E2, E3, E4. Fantastic. The assumptions made in this problem, well, we assumed all the resistances are probably equal in our gauge, that we're only basically pulling a switch over one strain gauge in particular. What else? Standard configuration, that's another one. And I think those are some pretty good assumptions. And that we're elastic as well. That's actually a big major assumption. All right, finally, so we have, let me call this A, B, C. So we have strain rosette between B and C, 76 degrees. Between A and B, 17 degrees. So we have basically a strain. We're going to call that. So in this problem, I'm actually going to clear EB. So now my EA is 376, 125, and then 25. So I always like to go counterclockwise. So in this problem, if I'm looking at my gamma over 2, if I'm looking at these values, this is EA, this is EB, this is EC. I always like to draw the circle, again, rotating counterclockwise, 2 theta, center, radius. So I'm going to draw everything relative to EA. So my first equation is going to be, so I've got those values here, microstrain. So I'm going to call this EA. Now the angle between A and B is just 17. And then the angle between A and C is going to be 17 plus 76 times 2. There we go. Solve these with 3 equations, 3 unknowns. There's our values. If we want the angle, I'm going to go ahead and pull out this angle right here. This is going to be my angle to principal stress, so 31 degrees. What about the value of a maximum shear strain? That's a great one. So engineering shear strain will just be the radius right here. Fantastic. That's it. Thanks, and we'll see you in the next exam. Bye.